Hello everyone. In this video, we're going to talk about binary. Now, you might think, why are we talking about binary so late in the semester, and why is it in the string unit? Well, I like to wait to talk about binary because once we've learned enough about for loops, while loops, strings, if statements, etc., we can implement algorithms that will convert decimal numbers to binary and binary numbers to decimal. So it's a really great application of all of the topics that we've learned in the course, well, most of the topics we've learned in the course so far. So that's why I like to wait to cover binary till the end of the class. It's also kind of a fun topic, so it's nice to have towards the end because it's not too stressful during the time we're getting close to finals. So let's take a look at the notes for today. We're going to review the decimal number system. It will help us when we begin to talk about the binary number system. We'll learn how to convert binary to and from decimal by hand, and then we'll write algorithms that can do this conversion for us. So for the warm-up task, go ahead and open a file called binaryfun.cpp in gedit, and in main, copy and paste the following code, run the code, and then answer these questions down here at the bottom. See if you can figure out the answers to question 2, and see if you can write code for question 3. So the answer to the first question is here. This is what the output looks like. The next question asks us if we can figure out what the 0b represents. Well, as you might be able to guess, based on the name of our file and the name of our lesson, the 0b represents binary. We've actually seen something similar to this 0 then a character before a number. For example, do you recall when we were printing out arrays? Say we had out nums, where nums is an array. This would print out the memory address of the first element of the array, and it was usually some kind of number like something like this. Doesn't matter what these numbers are to the right of the x. My emphasis is on the point that it started with a 0x. The 0x, or the 0b, is used to denote the base. This is a number in base 16, which is called hexadecimal. The numbers in our warm-up task are 0b, which is binary, base 2. So everything to the right of the b is the binary number. Like this is the binary number 0, this is the binary number 1, this is the binary number 10, so on and so forth. So when these are printed out, they're being converted to decimal. So, for example, the binary number 111 in decimal is 7. So essentially what I've listed out here are the counting numbers from 0 to 7 in binary. The last question says, add another cout statement that prints 8 using the 0b notation. Well, you don't know how to convert binary to decimal yet, but you should be able to see a pattern here. If you haven't figured this out yet, go ahead and pause the video and see if you can detect the pattern. Once all of the ones are filled up in a certain position, then the next one is used and the rest become zeros. For example, when the first one position is filled up, Then the next one started to use until those are filled up to ones, and then the next one is used, the rest are zeros. So here we have 0B, 1, 0, 0, 0. This is 8 in binary. And I should change my output over here. Great. That was a little preview into the binary number system. Now let's learn all about the binary number system. To do this, we're going to review the decimal number system first. So let's review decimal. In some ways, this part of the lesson is going to feel like you're back in elementary school. But it's a good review, and if you fully understand what we're about to review, then you'll be able to apply it to binary, no problem. Excuse me. Okay, so decimal is base 10. Therefore, it uses the digits 0 through 9, 10 digits for base 10. It's a positional number system, which means each position of a decimal number digit means something significant. For example, let's say I have the number 346. Now, when you were back in elementary school, what was the position the 6 is in called? It's called the ones position. And the 4 is in the tens position. And the 3 is in the hundreds position. Well, those ones, tens, hundreds, thousands, etc. are based on powers of 10. The ones position corresponds to 10 to the 0 power. The tens position corresponds to 10 to the 1 power. And the hundreds position corresponds to 10 to the power of 2, or 10 squared. So on and so forth. So we can decompose the number 346 to be the summation of its individual parts. For example, 346 is equivalent to 3 times 10 squared plus 4 times 10 to the 1 plus 6 times 10 to the 0, which is 300 plus 40 plus 6, which is 346. Now, it's much shorter for us to write 346 than it is to write this summation of products. But the summation of products is going to help us convert a binary number into decimal. Okay, we are now ready to begin our discussion of binary. Binary is base 2. Therefore, binary only needs 2 digits in order to represent its numbers. And those 2 digits are 0 and 1. Like decimal, binary is also a positional number system. So let's say, for example, I have the number 1101. Now, unless I tell you this is binary, you might think this is the decimal number 1101. So typically we put a little number denoting the base in the bottom right part of the number. For example, this is 1101, the binary number, so I'm putting a little 2 down here. This is 346. the decimal number. So I'll put a base 10 there. That's one way that we can use to distinguish our numbers so that we interpret them correctly, which is kind of like the 0b and the 0x that you saw in the code. Okay, so this is the positional number system. So this 1 is in what position? This is in the 1's position. This 0 is in the what position? This 0 is not in the 10's position because we're dealing with powers of 2. This is in the 2's position. And this 1 is in the 4's position. And this 1 is in the 8's position. So these position names are coming from powers of 2. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, so on and so forth. We can write this number as a summation of its parts, and then we'll see what this number is in decimal. So this is 1 times 2 cubed plus 1 times 2 squared plus 0 times 2 to the 1 plus 1 times 2 to the 0. 1 times 2 cubed is 8. 1 times 2 squared is 4. 0 times 2 to the 1 is 0. 1 times 2 to the 0 is 1. 8 plus 4 is 12, plus 1 is 13. So we just saw an example of how to convert a binary number to its decimal form. What we do is essentially sum the products of the binary digits and their power for that position. So if we head over to the browser, we could type in binary to decimal converter, and we could see an algorithm in action which can convert a decimal number to binary and a binary number to decimal. So let's convert 13 to binary and check our work. It looks like 13 in binary is 1101. Awesome. Now let's take a look at the general algorithm behind how to convert a binary number to decimal. Here's our general algorithm. We want to perform a summation process where we walk through each bit in the binary number. If the bit is a 1, we want to add a 2 raised to the power of I to the accumulated sum, where I is the position of the bit. So why don't you go ahead and head over to the VM and work on this task. It might seem kind of daunting, but I'm sure that with your strong problem-solving skills that you've developed over the course of this semester, you'll be able to tackle it. Go ahead and write an algorithm that converts binary to decimal. Specifically, this should be a function that accepts a string representing a binary number and returns an integer representation of that binary number. And remember, here's your general algorithm here that you're working to provide a C++ implementation of. And you can always return back to the steps that we took here in order to apply this conversion process. I've declared a variable called decimal, which is going to store our summation. Which means somewhere in between declaring the variable and returning the variable's value, we're going to have some sort of loop that's going to walk through each bit and figure out what the value is we should apply or add to decimal. So it looks like we're going to have a variable I, which we're going to be the power that we're going to raise to 2. So let's go ahead and declare an integer variable I, as well as a variable called power of 2, which we can use to represent this value, 2 to the I. Okay, so in terms of our string, it's going to store a binary number like 1101. Now, the power of 2 is going to be the length of the string minus 1 for our first digit. Recall that as a string, our valid index positions are 0 up to n minus 1, where in this case n is 4, so 4 minus 1 is 3. Our powers of 2, however, go the opposite. They start at n minus 1 and end at 0. So there are a few different ways to solve this. What I'm going to do is I'm going to use the power of 2 variable we just declared to keep track of this power. I'm going to start it at n minus 1, and I'm going to subtract 1 each iteration of the loop. I'll start at 0, and I'll add 1 each iteration of the loop in order to get this digit. So power of 2 is going to be initialized to binary.length minus 1. Highest power of 2, which is the power of 2 for the digit at index 0. Now we'll go ahead and just walk through each digit in the string. So we want to test. If the digit at binary sub I is equal to the character 1, remember we're working with strings here, so if we index to get a single character, we'll have to compare it to a character. If it's 1, then we want to accumulate in decimal 2 raised to the power of power 2. And each iteration of this loop, we want to subtract 1 from power of 2 as we add 1 to our index. I'm going to need to include the CMath library in order to use POW. All right, let's try our function out. Let's pass in the string 1101 that we've done a hand trace of, and we know that it is 13 in decimal. And there we see 13. Awesome. We should try a few more values. Let's try 11111. It says this is 31. Why don't you go ahead and pause the video and check to make sure by hand that 11111 is in fact 31 in decimal. Okay, we've seen the conversion from binary to decimal, Now it's time to see the conversion from decimal to binary, which I think is a little bit more tricky. So we'll need a decimal number to convert to binary. Let's say we're going to convert the number 56 to binary. The first thing that we want to do when converting a decimal number to binary is figure out what is the largest value, the largest power of 2 that goes into this number evenly. We need to know this because that tells us how many binary bits we need in order to represent this number. So a handy way to solve this problem is just go through and list out the first couple powers of 2. For example, 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, and then we just keep doubling from here. So now that we have this little table, it's much easier to answer the question of what is the highest power of 2 that goes into 56? Well, the highest power of 2 that goes into 56 is 2 to the 5th, 32. So that means we're going to need to have at least 6 spots to store our binary number for 56. Now our task is, how do we fill in 0 or 1 for each one of these spots? Well, if we know that 32 goes into 56 evenly one time, we can put a 1 in the spot for 2 to the 5th because we know that 32 contributes to the number 56, or the power of 2 to the 5th contributes to the number 56. Then we subtract out 32, which undoes our summation, and we get 24. Now we kind of have a new problem. What's the highest power of 2 that goes into 24? It's 16. So 16 goes into 24 evenly one time. So we can put a 1 in the 2 to the 4th spot. We subtract 16. And we get 8. Now we have a new subproblem. How many times does 2 to the 3 go into 8? Or what's the highest power of 2 that goes into 8? Well, 2 to the 3 goes into 8 one time evenly. 8 goes into 8. 1 minus 8 is 0. Now we have a new subproblem. What's the highest power of 2 that goes into 0? Or we're asking ourselves, does 2 squared go into 0? Does 4 go into 0? No, it does not. Does 2 to the 1 go into 0? No, it does not. Does 2 to the 0 go into 0? No, it does not. And we can check our work that 1, 1, 1, 0, 0, 0 is 56 in binary by converting it to decimal. 2 to the 5th is 32, plus 2 to the 4th is 16, plus 2 to the 3rd is 8, plus 0, plus 0, plus 0. 6 and 2 is 8, 8 and 8 is 16, 1, 3, 4, 5. So it looks like this is good. Let's try a more complicated example. In the code, in the notes for today, I've converted 94 to binary. Let's try converting 94 to binary. Same thing. We've got to figure out what's the highest power of 2 that goes into 94 evenly. That would be this one, 2 to the 6. So we'll need 7 bits in order to represent 94 as a binary number. Okay. We know that 2 to the 6 goes into, We know that 2 to the 6 goes into 94 evenly, one time. 64 goes into 94 evenly one time. We put a 1 here. We subtract 64, and we get 30. Now, this time, instead of saying, what's the highest power of 2 that goes into this number evenly, we can instead just start picking off each one of these powers of 2. Either approach works. It doesn't matter which one you use. If you'd like to think about this as kind of a nested problem where, okay, now we need to convert 30 to binary, you can go ahead and do that. If in this case, 2 to the 5 is not the highest power that goes into 30 evenly, it's 2 to the 4th, you would just put a 0 here, or you would just fill in all zeros to the left of the next highest power of 2. So I'm going to solve this one slightly differently. Now that we've tested if 2 to the 6 goes into 94 evenly, it does, we're left with 30. We'll just go to the next one. Does 32 go into 30 evenly? No, it does not. Minus 0, we're left with 30. Now we're here. 2 to the 4th, does 16 go into 30 evenly? Yes, it does. One time. Minus 16, give us 14. Does 2 to the 3 go into 14 evenly? Make more room. Yes, it does. Minus 8 is 6. Does 2 squared go into 6 evenly? Yes, it does. One time. Leaves us with 2. Does 2 to the 1 go into 2 evenly? Yes, it does. One time. Does 1 go into 0 evenly? No, it does not. Here is 94 in binary. And we can go ahead and check our work either with the notes or with our binary number converter, or by doing the conversion by hand. So we get 1 0, 4 1s, 0. 1 0, 4 1s, 0. Looks like our conversion is successful. So what's the general algorithm for converting a decimal number to binary? Well, it starts with finding the highest power of 2 that goes into the number evenly. Then it's a sequence of divisions and subtractions until your number reaches 0. Written more elegantly, here is the general algorithm that we follow to convert a decimal number to binary. Step 1, identify the largest power of 2 in the decimal number. Call this power n. For each power of 2, starting with n, 2 to the n minus 1, all the way down to 0. If the power of 2 goes into the number evenly, then we want to place a 1 at that power's position and subtract the power of 2 from the number. That's what we do here. If the power of 2 does not go into the number evenly, then we place a 0 in that power's position. So this is a little bit tricky to code up, particularly this first part right here. So I won't assign this as a task for you to try. Let's just code it up together. So this function is going to return a string accepting an integer. We're going to build a string representing our binary number, digit by digit. So I'm going to initialize it to the empty string. And then at the end of our function, I'm going to return it. That means that somewhere in here, we're going to be adding zeros and ones, one at a time, to our binary string in order to build out our full binary representation of our parameter decimal. Now, some other variables that we're going to need include an integer representing the highest power of 2 in the number, and another integer representing the current power of 2. So the highest power of 2 we can figure out by calling the log2 function from the CMath library. The log2 function returns the logarithm of base 2 of a number. So we want to pass in decimal. Let's pause here and just add some debug code where we can see what this value is. So let's call our function convert decimal to binary, and let's pass in 94. And it says here 6, which confirms what we found to be the highest power of 2. Wonderful. Now we're ready to code up our loop. So let's add a loop control variable, I. We want to run I from n all the way down to 0. It's going to be our exponent. So our n here is the variable highest power 2. We're going to run I all the way down, including 0. Subtracting 1 each time. So now let's raise 2 to I and store it in power 2. It may be more appropriate to call our power 2 variable power 2 value, so that we know it's not actually the exponent, it is 2 raised to the exponent. So it's the result of taking the power of 2. Or maybe we call it power 2 result. Whatever makes more sense to you. So we're raising 2 to the I, and now we want to ask, does this power of 2 go into the number evenly one time? A few different ways to do this. I'm going to go ahead and divide decimal by power 2 value. And see if it's greater than 0. If it is, what I want to do is add a 1 and subtract this value from the number. If it doesn't go in evenly at least one time, then I'm going to go ahead and set a 0. to this position in our binary number. So that for every iteration of our for loop, we're either adding a 1 or a 0 because that code is separated in the bodies of if-else statements. All right, we are ready to try this out. So for 94, we get 1 0 4 1s 0. 1 0 4 1s 0. Looks good. We should also test this with another number just to make sure that everything looks good. So let's pass in 13. We know that's 1101 because we did the conversion ourselves and we tested it. So that looks good. So we've seen how to do the conversion from binary to decimal and decimal to binary by hand. And we've seen how we can code up a solution using loops, functions, and strings in order to algorithmically make the conversion as well.